Hi and welcome to the Casted podcast here from IT University of Copenhagen. My name is Tore Husfeldt and here we try to talk about things related to the foundations of information technology. Today it will be a lot about history of information technology and how to think about emerging threats in cybersecurity. Here to help me talk and think about that is Rebecca Slayton. Rebecca is a professor at Cornell University at the Science and Technology Studies Institute and affiliated with a center, and I forgot the name.
Peace and Conflict Studies Institute and the Department for Science and Technology Studies.
Thank you very much. Rebecca, welcome to the show.
Thank you very much for having me. Yeah.
But you started as a physical chemist,
I did, yes. So I earned my PhD in physical chemistry. While I was earning my PhD, I became very interested in history of science and technology. I worked with lasers as a graduate student, ultra-fast lasers, and when my friends came to the lab, they always wanted to see my laser, meaning my weapon. They were referencing Dr. Evil, the movie Dr. Evil.
What else could a laser be than a weapon?
Exactly, a great weapon. Actually, they're terrible weapons. If we had my advisor almost left MIT over not getting good labs, because if you had a humid day, the whole laser would go out of alignment if things got too warm. You had to have perfect climate control. You had dust or air constantly blowing over the optics so that they wouldn't be disturbed by anything. Any change in temperature could mess the whole thing up. I thought, why? These are not good weapons.
However, at that time, I guess, no, actually before that, in the 80s, I guess, at that time, they were proposed as serious weapons in international warfare. And
they still are actually envisioned as wonderful weapons. And I became interested in why is it that we think lasers are fantastic weapons. Today, they are still pursued for that. Lasers do have one advantage over all other weapons, which is they are fast. They move at the speed of light. So with missile defense, which is what I ended up studying, you have a missile coming in very, very quickly, and you want to stop it before it gets to the target, and you maybe only have a few minutes. So a laser can get there in less than a second. You know, light goes, the speed of light would go around the Earth 7 times in a second. So it's very quick. The problem is they're very inefficient. So you pour lots and lots of power in, you get a tiny bit of power out. So they consume tremendous amounts of energy, they are unstable. If you have a cloudy day, your missile defense would not work very well with most kinds of lasers. So, but I became interested, why does the public think that lasers are fantastic weapons? Why are they always in the movies? Why are they in Austin Powers and Star Wars and Star Trek and everything else? And that led me to the Star Wars missile defense program in the 1980s, which was a program which President Ronald Reagan proposed to, quote unquote, render nuclear weapons impotent and obsolete. And he asked scientists, mainly physicists, was what everybody thought of, nuclear physicists, to give us the tools to make nuclear weapons impotent and obsolete. He never mentioned lasers in his speech, but there were a number of scientists, such as Edward Teller, Edward Teller was a famous nuclear physicist involved in the development of the hydrogen bomb, and he was promoting an X-ray laser as a new weapon that was going to turn things in favor of the defense against the offense. So he made a lot of promises for that. None of them came true. The X-ray laser has never been a good weapon, never really became very effective. But it nonetheless launched a major research program into laser technology and laser weapons, as well as other kinds of missile defense technology.
And I guess this is already 30 years or so into a longer conversation about how to protect, in this case, the United States against a missile attack from the country then known as the Soviet Union.
Absolutely. So the U.S. Certainly throughout World War II enjoyed not being bombed, having a certain kind of isolation. With the advent of nuclear weapons and then means of delivering them very quickly, that changed. So by the early 1950s, both the Soviet Union and the U.S. had long-range bombers that could go around the world in about 12 hours, which meant that, and a single nuclear weapon is so destructive that it could wipe out an entire city very, very quickly. The Soviets detonated their first atomic bomb in 1949, and that set off a huge, a lot of anxiety about that.
So the delivery system was then still planes, airplanes, bombers.
So once the Soviets launched the first Earth-orbiting satellite, artificial satellite, Sputnik, in 1957, it became clear that they were developing the kinds of technology that could launch a nuclear bomb up out of the atmosphere and around the world, and that would happen in about 30 minutes.
Yes.
So all of a sudden, within about 30 minutes, a major city could be completely, wiped out.
Yes, and Sputnik was a terrible thing for the American public because you could see it with your naked eye. You could look up in the sky in the evening, and there you saw this white dot slowly traveling across the horizon.
And so it wasn't as much as a shock to most of the scientists who were following the Soviet Union and who knew that the Soviets had very, very good scientists, and still do have very, very good scientists. But most of the public had sort of gotten complacent and was thinking, we're the best, we've got the nuclear weapons, the US had come out of World War II without a lot of the devastation that a lot of Europe had experienced. And so it was quite a shock publicly. So at that point, there was, that really escalated efforts to develop defenses, nuclear defenses that would protect the United States from nuclear weapons. Of course, today, I should add very quickly, missile defenses are used, actually, they're probably used more outside of the US than in the US, right? So they're used in places like Israel.
They're launched from Israel, yes.
Yeah, and places that are accustomed to getting not nuclear bombs dropped on them, but a lot of conventional bombs. South Korea, being very close to North Korea, is of course very understandably interested in a defense against nuclear weapons. Japan, very interested in that. So it's definitely not solely a US story, but in 1957, that was the focus, was how do we protect the United States from nuclear weapons?
And there were ideas basically shooting down the incoming planes or then later missiles that were launched from the Soviet Union to land on the US. And this seemed to be, I don't know, a computationally easy problem at the beginning until you started thinking about this? Because I want to turn this towards computation now, because there are several issues here. You actually need to build the rocket that takes out the other rocket, or whatever countermeasures you want to think, which is a physical thing that you need to launch and steer and control. But you also, the logic, the computational infrastructure of this also was a problem. And I guess in the beginning of the 50s, this was seen as an easy problem.
Yes, absolutely it was. So, or at least it was seen as something that could be managed fairly well with existing technology. You just had to build a big enough computer, a fast enough computer to do the job. And it's very different than it is today. So today, in 2003, when the United States went into Iraq, it deployed some missile defense systems to protect troops, also to protect Israel from bombing, and ended up shooting down a British airplane, a fighter plane, and a US fighter plane, and killing 3 people. And when that sort of thing happens today, the first thing people say is, it must have been a software glitch.
Yes.
Something went wrong with the software. We all know that software is buggy. We've all had our computers crash. And it turns out that's not how people used to think about computers. In the 1950s, people thought about computers as giant brains. They were going to be smarter than people. And you still hear that occasionally today, but most people are a little more skeptical about it today because they've interacted with these machines that don't always work so well. But in the 1950s, they were seen as something that would be very, very intelligent, very reliable, and software in particular was seen as the easy part. So at that time, the computer machines themselves, the physical hardware, was often breaking down. It was not nearly as reliable as it was today, and everybody thought, well, the easy part is the software, and it's going to be great because it used to be that we would build computers with analog machines, that you would literally create an analog of the physical world in a machine, and that was how you programmed it effectively, was you recreated the physical world and used that to make a kind of calculation. They said, now we don't have to do that. With digital electronic computers, we can make the same machine do all kinds of different things. All we have to do is tell it what to do. And the instructions we'll come up with ways of producing instructions very efficiently. It's just a kind of mathematics. It'll be very straightforward. Slowly that became called software. Historically, software has meant not just the instructions, the code or the information, but it has meant the people that program the computers, the manuals that tell you how to program the computers. Anything that's not a physical machine was called software. And that was seen as the easy part. initially. And that was the great advantage of electronic computers, is that all you had to do was give them a new computer program and they would do whatever you wanted. You didn't have to build a new machine.
And by that time, we had known that fact, which today is obvious. My children know this, only for maybe 8 years or something. I guess von Neumann's ENIAC computer was 43, 44 or something like that.
Yes.
So most people in the 50s, I guess, had never seen a computer. And those who had seen it viewed it as basically just a way of automating something that before that had been electrical engineering or control theory, I don't know.
Right, and for the most part, computers were giant calculators. Yes. They weren't things you interacted with, they didn't have cool screens. You gave it a problem and it gave you a number at the output.
Yeah, and the problem you gave it on a punched card or something which you fed into a mechanical device which read it off, and then you waited for sometimes hours or days.
Yes.
And then the system came back. Yeah, it was an a machine that transformed input to output and just computed, say, ballistic trajectories or weather models.
Right.
Or actually helped developing the nuclear bomb for the United States.
Yes.
That's actually how von Neumann's work was partially financed at Princeton.
Absolutely, yes. And that was one of the first things that was run on the first digital electronic computer was simulations for a hydrogen bomb.
Yeah.
Yeah.
So certainly from the point of technological history in the US, the development of the electronic computer and the development of the nuclear bomb is very tightly interwoven, both administratively, technically, economically, even scientifically. It's always the same institutes that try to do these things at the same time.
Now, scientists did recognize in the 1950s that the computers for a missile defense system would have to be different than these giant calculators because they would have to react in real time. They would have to track the missile as it was coming in and give out numbers immediately. They couldn't wait for a few hours and then tell people where to shoot the missile interceptors. And that was going to be a challenge. But it was a challenge they felt was very doable.
Yeah, just make a harder computer, I guess. If you looked at the development from 1930 to 1940 and then extrapolated that, it seemed plausible that you could make faster and faster machines that did this. There's an input-output problem. There's some kind of conceptual thinking needed to understand that now suddenly the machine has to interact with a computer with a human in real time.
Absolutely,
rather than being a fixed room-size calculator.
Right. Yeah, and so the problem of computing was seen as being, for missile defense, was seen as primarily building the machine. Build a physical machine that can calculate fast enough and do the right kinds of calculations. Software began to be recognized as a problem in the 1960s, but it was usually only seen as something that was a problem for interacting with machines. So the problem was, how do we make machines more interactive? And we worried about that for nuclear command and control, because we expected that people would be there trying to decide whether to launch nuclear missiles or not. But with missile defense, we basically said, well, nobody's going to be in the loop. There isn't enough time for a human in the loop. So it'll be automatic. Software isn't a problem because what software meant at the time was it was about humans interacting with machines as opposed to instructions coded into a machine.
So is that the dichotomy between command and control on one side and what human-computer interaction on the other, or am I mixing up concepts now?
No, that's right. So a lot of the early research into human-computer interactions was funded by the US Defense Department, in large part because they wanted nuclear command and control systems to be better. Mm-hmm. And not just nuclear command and control, all command and control systems, because we ended up fighting a lot of non-nuclear wars, a lot more non-nuclear wars than we have nuclear wars. But that was the key problem, was how do you get the right kinds of information to the officers who have to make decisions? How do you present information to them in a way that they can process easily? And all of that eventually led to what we now see as interactive computers, very interactive computers. It took a very long, circuitous route to the personal computer. It didn't go straight from military computers to personal computers. But a lot of the research, things like a mouse, graphical user interfaces.
Or just a screen.
Yeah, a screen, which is a kind of graphical user interface. One of the things they had for air defense, which was the precursor to missile defense, was light pens with a big cathode ray screen where people could go and touch the pen to the screen and interact in real time.
Very cool.
With it, yeah. So it's sort of the world's earliest touch screen,
I
so
want
to
one of
speak.
those.
Yes,
excellent.
Exactly.
So I guess then you discussed whether you needed 20 programmers or 200 programmers or even 2,000 programmers to do this, because it turned out to be harder and harder and harder.
Much harder.
And there wasn't really a profession associated with this. Programmers were all kinds of persons, converted mathematicians or just old-fashioned, I guess, computers. So, yeah. I guess computers at that time was a human profession, right? The IEEE, one of our professional magazines, the IEEE Transactions on Electronic Computers, changed its name to IEEE Transactions on Computers in 1967 or something like that. Because by that time there were no computers left, there were only electronic computers, and the word computer then came to mean electronic computers.
Exactly.
But by the 50s, or even before that, computer was a human profession, somebody who just crunched numbers.
Absolutely. So a lot of the calculations done for building atomic weapons were done by human computers, who were mostly women, actually, sitting at tables using slide rules and various machines to make computations and create ballistic tables for soldiers firing, things like that. And basically what the electronic computer did was to take over some of that work. Women were very involved in the early programming of these machines, which early on, the way that the first electronic computer was programmed was actually to connect one output to another output, right, with big cables. And women were very involved in that. Because it was something nobody had ever heard of, and it was strongly associated with clerical work, secretarial work, a lot of women were the earliest computers. Now, when I say that, I don't mean to say that they were just secretaries or to diminish the work. In fact, many of them had math degrees, were advanced math degrees, and they were just told, figure out how to make this thing run.
Yeah, secretarial work is hard. It's cognitively challenging.
Absolutely.
It needs discipline and hard work, and you can't make many mistakes.
And some of it was actually quite mathematical. So they actually had PhD holding women in mathematics.
And I guess one of the early conceptual breakthroughs in programming computers is due to Grace Hopper, a woman who wrote the first compiler or invented the idea that you could translate the instructions for the computer in the, let's call it, in a language that is easier to understand for humans, more or less mechanically. Mechanical is again a loaded word here. Automatically into instructions that can be fed into the machine.
That's right, yes. And so she was one of the first programmers, and she did very groundbreaking work in terms of developing new computer languages and developing new methods for programming. And a lot of women did. Now, as computing and as programming began to professionalize, as is often the case, as an area of work becomes more prestigious, a lot of times women start to get pushed out of it and men start to take it over, and if the pay goes up, men tend to get those jobs more and more. So that happened sort of in the late 1960s, more and more. There was an effort to professionalize programming.
But there still was not an academic discipline associated with it. There was not a profession.
No.
What it meant to be a programmer or coder was still very unclear, as it is, I guess, today.
In some ways it still is today, yes.
Because unlike doctors, people who program computers either have a PhD in computer science or not at all.
Yeah, and many of them don't even have to finish high school, and they can go make loads of money.
Yes.
A lot of hackers today make loads of money without a high school diploma or without a college diploma. Now, some of them do, in fact, get those degrees.
I have one, yes.
And go on to be hackers. But if you're good at it, you don't have to. And because you have the skills that are in high demand, you can make a lot of money.
But very unlike doctors, right? There are not many high school dropouts who are neurosurgeons.
That's right.
Because we have some kind of societal agreement that in order to become a neurosurgeon, you need the credentials that you actually learn this.
So sort of the ultimate paradigm of a professional is a group that, first of all, it establishes a curriculum, a training regimen that must be followed, certifications to certify professionals as properly trained, and then the ultimate sign of a profession is when they get a government to say, nobody can practice this kind of work unless they have a degree, a certification from this particular profession. So in the United States, it is illegal to be a doctor without having been certified by the American Medical Association. And I'm guessing it's similar in Denmark.
It's very similar. Yeah,
yes.
Of course, we're doing our best to give people degrees here because this is a place of higher learning. So but there are certainly many competent people who don't have any degree in computer science or software engineering or anything. We don't even know what that really means, these terms. So I want to get back to that, because the interesting question appearing here is, would then the world, since we're obviously having some kind of software crisis, where now everybody, including my children, knows that software is almost always certainly critical and sometimes doesn't work. So could we actually fix that by then just enforcing people to be, or programmers to be more like doctors? And I guess I want to get back there in a minute, but let's get back to the 80s first, because even though the Patriot missile system exists, I guess the Star Wars project never really became what it wanted to be. There are no satellites in space shooting down intercontinental ballistic missiles with lasers.
Right. So what Star Wars ended up being was a big research funding program. It funded a lot of research. Nothing was directly deployed. So now some of that research has eventually gone into the field. Most of it has not. We don't have any beam weapons that are really operational and getting used a lot today. We have some that are very close to being operational, but the test that they'll always have to stand is, are they better than an ordinary missile interceptor? And in terms of price for protection. If they're not, if we can do just as well by spending the same amount of money on missile interceptors, why spend the money on a laser, right?
Or in this case, just as badly, because had the Soviet Union launched 100 nuclear weapons at the US, I guess it would have been game over.
That's right.
Because this is a problem that we never solved, or the US never solved.
No, and
despite 30 years of research.
And nobody in the world has ever solved it. We are still, everybody in the world is still vulnerable. Everybody in every country is still vulnerable to nuclear weapons. So I think the US currently has a system that with a testing record of about 50-50. So about half of the time it succeeds in intercepting the missile, the test missile that's coming in. But bear in mind that those are usually very tightly controlled conditions where there's a fair amount of information. You may not know the exact moment at which the missile is going to arrive, but you know sometime in the next day to look for it. And it's only one missile at a time or two missiles at a time. When you consider that the Soviet Union and the United States both still have thousands of these missiles, any one of which could completely demolish a city and much of the surrounding area, there's just no defense against it. And I'm very skeptical that there ever will be a defense against. You never say never, but nobody has proposed anything or has a realistic proposal for something that would really get rid of those, aside from us just getting rid of them. Just agreeing to turn them into...
I guess on the list. 1st of July 1968, when the nuclear non-proliferation treaty was signed. Exactly. I was born that day. That's the one date in history I know. Yes. That's the one day in history I know.
It's a good day to be born.
Yes, absolutely. So we didn't actually kill each other during the Cold War.
No, fortunately.
Fortunately.
We came close.
But what interests us here is the discussion about this technology which was proposed, funded, and might have had catastrophic or positive effects on humanity. So and it's one of the earliest examples where there's a more or less formalized interplay between governing bodies and scientists, whatever that meant. I guess scientists meant a handful of theoretical physicists. You mentioned Teller.
Exactly, very elite physicists. So at the end of World War II, first of all, World War II was one of the first wars where scientists were put in charge. And engineers as well, I should say. And Vannevar Bush was a famous engineer in the United States who basically designed the U.S. Strategy for winning the war, for doing research and development that would win the war. Most people say that nuclear weapons ended the war, the atomic bomb ended the war, but radars won the war. And so there was all of this research going on, and near the end of the war, President Roosevelt thought very, very hard about what we should do with this enormous scientific research establishment. And basically there was a decision made that we would continue investing very heavily in science and engineering because of a belief that it was going to transform, not just bring security, but bring about health, bring about better agriculture. And at the end of World War II, physicists in particular, as the people who had helped develop radar and develop nuclear weapons, were much elevated in politics, in policy. After Sputnik, there was a group created, the President's Science Advisory Committee. There had been presidential science advisory committees, they weren't called that, science advisory committees with the president's ear before, but that really made sure that the President's Science Advisory Committee had, in that case, President Eisenhower's ear. He also elevated them, gave them more authority because he wanted to control inter-service rivalry in the military bureaucracy, where the Air Force and the Army and the Navy were all saying, no, we want our weapons, and we don't want them to have their weapons, we want ours, and so then we were going to get 3 times as many weapons as we needed. So physicists became the dominant scientific advisors because they had been associated with nuclear weapons and building them. Now, some of them knew a little bit about computers. They certainly were associated. They knew that they needed computers to do their research. They knew that by the mid to late 1960s, they knew that computers were not always being built on time and delivered on time.
Imagine that.
Isidore Rabi, famous nuclear physicist in 1967, on the NATO Science Committee, said, you know what we really should do is we should get together a bunch of software experts, computer experts, and have them figure out why it is that we're never getting the computers we need on time. That started the world's first software engineering conference. It was a NATO-sponsored group. It was international. It was held in Garmisch, Germany in 1968. And there they declared that there was a crisis in software engineering and there were several dimensions of the crisis. One was that software was usually delivered late instead of on time. It usually cost much more money. And third, it usually did not perform as planned or as expected. It had unexpected bugs and glitches and problems. And so they said, well, we're going to create a new discipline, a software engineering discipline, to solve this problem. And over the next decade or so, there were only really 2 NATO-sponsored software engineering conferences, in part because after the second one, nobody could agree on what to do. But the US government invested a lot of money in software engineering in the 1970s, in part because it was worried about the growing costs of software. And there was this idea that in terms of computing costs, software was occupying a greater and greater fraction of the computing costs. And unless we could figure out how to bring those costs down, we were going to go bankrupt. We wouldn't be able to afford the computers we needed.
Yes. And this was still before the internet, more or less. I mean, the internet started existing there, but it didn't dominate our conceptualization of what computers are, what software are, as much as it is today. So today, software engineering has to tackle even harder problems of security, where bugs no longer just are a result of human error, programmer error, but actually malicious attacks from the outside, constantly changing environment where the software has to run, and so on. So rather than solve the problem with that single conference, it turned out that it just pointed to something that became much worse.
And one of the things that they said at that first conference is, it's not that we're doing so bad, we as software engineers are doing so bad, it's that the expectations for computers keep growing and getting larger and larger. And our peers in hardware are building faster and faster machines, and we can't keep up. And they're building machines that can do more and more complicated things, and we can't keep up. And that's probably still true today in a lot of ways. That what we do with computers now and what software engineers do is far more complex than ever before, but we keep asking more of them. And we want it to be better and faster and on time and to never fail.
And we can do amazing things with software today, like the Angry Birds are recognizing cats, but they also fail in more and more interesting and catastrophic ways. And as we move more and more infrastructure and more and more decisions to software, these failures become, in some sense, more and more critical.
Yes, absolutely. And that was something that they were concerned about even in the 1960s as well, was that already models of airplanes, for example, were being computerized. What if the computer model of the airplane made a mistake and then the airplane failed in some way? Air traffic control systems, they were already starting to computerize aspects of that. What if the computer delivered a glitch and all of a sudden 2 airplanes collided because the computer had things wrong? So these have been concerns for a very long time, and those concerns underlay this area of safety critical computing. So the computers that run nuclear reactors, the computers that run pacemakers in people's hearts, the computers that run power grids, airplanes, trains, where human lives actually depend on that software being correct. A lot of research has gone into making sure that software is in fact reliable.
And by now it is actually surprisingly reliable. There are pacemakers. Entire cities have their traffic infrastructure now running by software. And this more or less, it more or less works.
Yes.
So these are safety critical systems, which is, I think, a useful concept here. And we have become somewhat better at building these using software engineering processes that very much rely on us rewriting or patching or reacting to errors that appear.
Right.
So, yeah, talk a bit about that.
Yeah, so systems they are never reliable when they are first produced. They become reliable by being used operationally and by having opportunities for things to go wrong and then get corrected.
And the reason for that is just because people like me are stupid, or because...
No. Software engineers are very talented, organized, well, not all, but most, the cream of the crop, very talented, organized engineers. But it's an incredibly complex system. Software is incredibly complex. So there are at least two things that are really different about software engineering and hardware engineering. One is that when we engineer physical systems, things like buildings, we have continuous mathematical functions that predict how they will behave. Okay, so we know what the laws of gravity are. We know what the force equations look like. And so we can kind of predict what's going to happen if we build a machine in a certain way, and we can model it and do a very good job with that. We don't have laws that predict how software will behave. Now, we have developed, since the 1970s, some rules that will predict how long it might take to build software, right? If it has a certain length, how long, and it's a certain level of complexity, how long will it take, how many people will it take, how many years will it take. And so that area has grown very sophisticated. But in terms of predicting exactly how it will operate, you don't have that. Now, the alternative to that is to use a kind of deductive logic to make sure, using sort of finite, discrete mathematics, that the system will behave as it's expected to behave. But it turns out that it's very, very difficult to prove that a computer program will behave as it's expected to using deductive logic. And there's been a lot of progress in that area. The US Defense Department recently developed a drone helicopter where the operating system for it was proven to meet its specification, and hackers were unable to hack it. So that's probably the most secure system we've ever built. Mm-hmm. It's still probably a lot simpler than the operating system that you and I use on our computers every day.
Oh yeah, but that's huge, and that is the Linux kernel, which is updated thousands of times per. Well, it's many times. It's enormous, and it's constantly evolving. But so, okay, there was some really useful concept on the table here. We talked about security, so some kind of resilience towards a malicious attack from the outside. We also talked about proving logically as a piece of math the functionality or the correctness of functionality with respect to a specification.
Yes, right.
But of course, software then has yet another problem in that it interacts with the outside, and that's also very, very hard to model, because then you would have to model not only biology, but even maybe one of the hardest disciplines, namely sociology. Or find a good model. So our dream would be to have a good model of how people behave individually and in groups in all kinds of weather situations that is as easy as the laws of physics for when buildings fall down.
Yes.
And that's really hard.
It's very hard, and it's also hard to know what the right specification is. So right now we have a lot of computers that are running physical machinery. They're called industrial control systems computers, right? So the computers that run the power grid, the computers that run manufacturing plants, petroleum plants, those sorts of things. Those were designed very deliberately. The specification said, we don't want passwords. Why? Because if something's going wrong with this machine, people could be injured, something could explode. Anybody who's an operator on the floor has to be able to come in, and they can't be locked out because of the password. They're not designed to be encrypted. The specification is in a way deliberately insecure. So we specified things without thinking about security. Now those computers could have been proven correct according to their specification, but they would still be insecure because we didn't anticipate particular threats.
We specified functionality. We specify how this thing should work in the imperfect conditions. But we fail to specify, or maybe we want to avoid specifying facts like people shouldn't just be able to turn it off willy-nilly, because on a manufacturing floor you actually want people to turn it off very quickly.
If they need to. Yes, exactly. And so it's not just predicting how people will respond, but understanding what the right specification is. And that ultimately is a human, social, intellectual problem. Figuring out what you really want this machine to do and what you don't want it to do under any certain circumstances.
And that's even assuming that there's only one person who knows. I mean, it's also a political problem, because there might be many different
visions.
Aspects, visions of what this thing should be.
Should do, absolutely.
And I guess certainly for national defense, this is obviously a political problem with many, many, many parts, including the populace involved in this. And making a hard decision, such as observing that not defending yourself against missile attacks is actually a better thing than defending yourself. Yes. That's a surprising conclusion.
It's a strange, bizarre conclusion. Yeah. I mean, and the Soviet Union argued this until the late 1960s. Quite reasonably, they said it makes no sense for us to say we should give up defenses. The problem is not the defenses, the problem is the offenses. And what scientists very slowly concluded, in part by talking to each other and thinking about, well, what would we do? What do we do when Russia builds nuclear defenses? Well, we build more offenses. What are they going to do if we build defenses? Well, they're going to build more offenses. And what we figured out fairly early was that defense was a lot more expensive than offense. Mm-hmm. So if we spent $1 billion on defense, for example, it might only take $1 million to overcome that defense. And then, so just in terms of money, it made no sense to invest in defense. Instead, what we came to rely on is we will threaten each other sufficiently that neither side will ever attack. And that's part of why, and not only do we have to threaten each other to make sure that they don't attack us first, but we need to make sure that if they attack us first, we can still do a second strike and take out their second strike capability, which is why we got a ridiculous, and still have a ridiculous amount of nuclear weapons, enough to annihilate all human beings, because we had this sort of logic that we had to make sure that we could threaten each other to a very high extent.
And this seems to have worked, but now of course there's a completely different threat model where there's now not a large economy and not a large nation state with hundreds or thousands of nuclear warheads, but single warheads or bombs just going off somewhere, and we don't really know what to do about that.
And actually the massive nuclear threat is not gone. The Soviet Union and the United States still do have thousands of nuclear weapons that they could launch at any time. And I hope that our military and political leaders are smart enough and calm enough to know better than to do that. Mm-hmm. To launch even one would be catastrophic. But there's also the possibility for errors, for people to misunderstand, for example, for the US to believe that it is under attack and therefore to attack when in fact there is no attack, and then you have an accidental nuclear war. We not long ago had a situation in which an airplane sat in the US military, sat on a runway for 12, 15 hours before people realized it had nuclear weapons on it, ready to go. So when you have thousands and thousands of nuclear weapons, and when you run operations so that you're ready to use them at any time, accidents are very likely to happen. And a lot of accidents did happen. So we did okay during the Cold War, but we also had a lot of accidents.
And there were lots of close calls
as
well,
including
false positives that just did not have an effect because a human said, no, this must be a mistake.
Absolutely. The US accidentally bombed itself. Oh. A plane crashed, and the bomb fell on, I think it was North Carolina. Fortunately, the bomb did not go off. Oh. So we got lucky.
Oh, because of error, yes.
But when you almost drop a nuclear bomb on yourself, that's an indication that there's a problem.
So back to this conversation between science and politics. That was had by physicists back in the 80s, because I guess the software argument was still too weird. There was nobody in the 80s saying that our missile defense system can never work because it relies on software, and software will always malfunction in the at just the wrong moment.
Right. So in the 1980s, that argument started to be very persuasive for the first time, and that's what got me really interested in this area. When I started studying Star Wars, I thought, I'm going to study the physicists and their arguments about lasers and why the lasers aren't powerful enough to overcome the entire Soviet arsenal. But then I discovered this very interesting argument being made by computer scientists, which took a very different form than the physicists. The physicists tend to talk about laws of nature. They tended to simplify the problem, partly so that they could say, we're not being pessimistic. We're assuming that all the technology works right, And still, the laws of physics tell you that this is how good they can do, and they cannot render nuclear weapons.
So they have very crisp, clear, sometimes single formula,
Absolutely.
continuous expressions that say even if everything works well,
Yes.
then
it's impossible.
the laws of thermodynamics or whatever it is.
Or just the sheer destructive power of nuclear weapons. Maybe you can get one nuclear weapon, but guess what? There's 1,000 behind it, and that's the end of the world. Computer scientists instead said, you know what? The problem is the complexity. We can't just sort of wish that away. The problem is that we don't know how to build software that will work right the first time it's used. The only way that we become to trust in software is to use it in real life, and that's why we have beta versions of software, because we expect that they're going to give us trouble and that they're not entirely reliable. And then the more we use it, the more we discover the kinds of things that can go wrong, and we fix them, and they get better. But we're not going to do that with a nuclear missile defense system. We're not going to have trial nuclear wars. You will have testing, but that testing is always going to be limited, and will it ever be realistic enough?
You sort of rely on the fact that the other side plays by the rules that you just invented for a testing scenario.
Exactly, exactly. So we're going to try to imagine all the things that the enemy can do. Well, there's a lot of things that people can think up to do to each other, to fool each other.
Then you still have to run the entire thing with simulating nuclear explosions in the stratosphere to see what effect that has on the laser targeting system.
What effect it could have on the computer systems.
Yes.
I mean, electromagnetic pulses can wipe out your electronics as well, right? So of course you'd then have to harden it in a bunker somewhere. I mean, the physical problems in theory could sort of be dealt with, but this complexity problem would not go away, that you wouldn't be able to test it adequately. At least that was the argument made by, I would say, the majority of computer scientists in the 1980s. There were some, however, who said, you know what, no, you're being pessimistic. We're engineers. We know how to do better. We'll figure it out. We'll figure out how to make it reliable, even though we can't do fully realistic testing. And part of the question would be, well, what's realistic enough? When has it been tested enough? So there was this debate within the computing community. What struck me when I started studying it was that it was the first time that it really started to influence policy. So in the 1980s, when this debate happened in the computing community, policy actually changed. The US Congress issued a study, or commissioned a study by the Office of Technology Assessment, Congressional Office of Technology Assessment, into the software problem. They concluded that there was a significant chance of what they would call a catastrophic failure, meaning some unexpected set of interactions causes the whole thing just not to work. It's not like a 10% reduction in effectiveness, it just doesn't work at all because the computer crashes. And policy actually started to change. People started saying, you know what, instead of coming up with all the weapons first and saying, here's the weapons we want to use, now let's write the software to make them all interact properly. We have to think about, what is the information processing problem? What is the information that needs to come in? What has to be calculated? And we should develop weapons that make it simpler to process the information. So instead of having the physical weapons first, and then you write the software so that they all get knit together and they all talk to each other right, we think about, well, what's the information processing problem? Now let's develop the weapons around that. Out of that came a program that was part of the rationale for doing Brilliant Pebbles, is what it was called,
yes.
Which didn't go very far, but was the idea that you'd have...
This is the Bush administration?
Yeah, it was proposed near the end of the Reagan administration, but then, really it took off in the Bush administration. I think that's right. I think it was during the Reagan administration that it was first proposed. But the idea was that you would have thousands or hundreds of thousands of sort of smart interceptors that would all kind of be interdependent, and that they would figure out the right thing to hit.
And they sounded cute.
They're very cute, right? It was a very cute program. Mm-hmm. It was, in a way, it was also Lawrence Livermore Nuclear Laboratory's effort to keep a missile defense program going after the X-ray laser turned out to be utterly useless. And they needed to have something to keep their research program going, so they tried to shift attention to Brilliant Pebbles. But the reason that that was taken seriously, to the extent that it was taken seriously, was that it would have simplified the information processing problem by distributing the weapons all over the place, instead of requiring that a single weapon get it right.
Yes. So there is more resilience built into the system.
Exactly.
And there's a clear computational perspective already in the hardware design.
Yes, exactly.
Very nice. So, so the only place where I'm sort of injected myself into a discussion between science and politics is another safety critical system, which would be election systems. So that has many of the same properties.
Yes,
that it's software that has to run exactly once, perfectly, untested, and it's very difficult for us to convince politicians, in particular politicians who are invested in increasing digitization in society, for instance, to explain to them that this is not a problem we can solve. We can't think very hard and write software that runs, where the beta test version runs flawlessly on election day, and then it's not going to be touched for 4 more years, and then it's going to run on the hardware, which by then is obsolete. This is very, very hard, because the utopia or the fascination by this, the blind faith in the fact that sufficiently clever people should be able to write a piece of computer code that is just perfect from the first moment is still there. I mean,
yes,
it absolutely still exists. And I guess it's, in some sense, of course, software is more like the law, right? That you have a complex system of rules that should regulate the behavior of people in some kind of formal way, but which is probably broken from the moment it's slightly broken from the moment you build it, and then it needs to be constantly re-evaluated and changed, and be subject to testing.
Yeah, and the software that you need for an election system is actually relatively simple.
Oh yeah.
I mean, all it has to do is add one, right? Add one every time that somebody votes for somebody.
Check that you don't add the same one twice.
Twice, exactly right. But proving that nobody has tampered with it, right, is much more difficult to do. Yeah. And it comes down to who's in control of the machines. Ultimately, it's a social problem, right? Like, who's in control of the machines, who builds them, who checks them.
Even if you have a proof that the software is correct, you have no guarantee that that is the software actually being run on the machine that you vote on.
Somebody didn't change it. You know, every voter can't go in and check that. It's too, it's literally physically removed from us. Yeah.
But it's the same kind of safety critical system that is not only safety critical, it's safety critical at very, very brief and discrete moments in time, and then it's not being tested. Unlike, say, a pacemaker or an aircraft system, which at least are constantly being, or the payment system at your internet bank. Yes. These are constantly being tested.
Absolutely. I wouldn't really think of a voting system as being safety critical, just because no human lives depend on it immediately. Now, down the road they might. You can say, if you elect the wrong person, he's going to start a war, and that is frightening.
You have a better word for me than safety critical for this then? Critical infrastructure?
It actually has recently been considered, it recently was declared a part of critical infrastructure. After controversy over the most recent US election, the United States declared it. I don't know how it is in Denmark. Do you call things critical infrastructure here?
I don't know if that's a protected term yet.
Okay. But yeah, so in the US there are sort of 16 different critical infrastructure is just a set of categories that we came up with. Things like nuclear facilities are a critical infrastructure.
Utilities.
Transportation, energy is all lumped together. So that would be electricity, oil, gas, government buildings. Like there's a whole bunch of different critical infrastructures. And very recently, voting machines and voting infrastructure was recognized as a critical infrastructure, partly because of the questions around the last US election. So it's interesting, this issue of cybersecurity, because there's no evidence that the election machines were tampered with during the most recent US election. And that's probably reliable because intelligence services watch that, and they would have had to interfere with a lot of machines. So it's possible that there was some conspiracy, but there's not a lot of evidence that it happened. But what we do know happened was that there was a sustained effort to deceive and manipulate people into having particular political points of view, and that a lot of that effort came from outside of of course, all political campaigns do that.
We all do that, yes. That's just part of the public sphere and propaganda.
Politics always does. Yes. And of course, the US has tried to influence politics abroad, and Russia tried to influence politics in the United States. What's new about it is how it leverages social media now and people's tendency to only read what they want to read and to stay within their social network. Not only was it the case that Russian propaganda networks were delivering fake news and coming up with fake news, but that they were tampering with algorithms to increase the number of hits and visibility of particular stories. through sort of bots, through networks, a lot of different mechanisms. So that is new, and I think it's a big, difficult problem that we haven't figured out how to solve.
Oh, yeah. But it's still not even the hardest, because we're not even talking about maliciously attacking somebody else's computer, right? Because everything we talked so far, things fail to work just because of human error. Just because the software doesn't do what we thought it did, because there's a complicated new patch 4.20 at the socket interface, and that doesn't work with the other protocol of the bomb or whatever it is, of the radar or laser that it should interface with, and it simply doesn't work. Not because anybody tried to tamper with it, but because
accidental failure.
Accidental failure. Right now, thanks to the internet and thanks to us moving more and more infrastructure onto the same network, for instance, we are also opening ourselves to malicious attacks.
And a lot of those malicious attacks then take advantage of the unexpected and unknown mistakes in software. Yes. So most vulnerabilities in software, most of the things that hackers or attackers exploit are actually mistakes in software. So one of the solutions to that, some of these things are very well known and very easy to avoid, but we don't necessarily have incentives for companies to produce secure software. Partly because we as consumers don't necessarily want to pay for software that it costs a lot more if we don't actually know it's secure. And how do we know it's more secure? Right? You can't really know that until it's been out in the field for 5 or 6 years. So companies have an incentive to just push stuff out the door, to capture a large market share, particularly if you're a social media platform or something like that, where if you get the first 100,000 subscribers, you're going to get the next 2 million. But if you're late, you're going to miss that. So there's an incentive to push products out while they're still insecure and then fix them later. And that is part of why, so that there are economic issues, information asymmetry issues that lead to insecure computer software and hardware today.
But also governmental agencies that have to buy a new IT infrastructure for whatever administrative purpose they have are incentivized to take the cheapest option and take that.
They're almost required to.
They're almost required to.
Yeah, basically.
So it's not only private citizens who make stupid mistakes, it's also governmental agencies who make stupid mistakes because they're actually forced to do that or incentivized to do that. And then maybe if they're good little Boy Scouts, they pay some external firm to verify their software, so they have a piece of paper that says that now this software is absolutely secure, and then next week a patch arrives, and there's very, very little organizational capital gained by saying, oh, we have to throw the report out now because there's a new patch, let's install that. So this is really, really hard to think about.
Yeah. It's an unsolved problem, I think.
It is
a problem that we're going to be living with for a long time.
Exactly. I guess we have to view this as a reality that we have to cope with, rather than a problem that we can solve.
That's right. And I think that there are a lot of things that we can do better to cope better, but it's never going to be completely perfect because of this high level of complexity and because there will always be unexpected errors that somebody can exploit if they want to.
And the thing to focus on then would be some kind of getting back from that, as resilience or something like that has to be built into the system rather than
There's a lot of different approaches. So resilience is one of them, to basically say we accept that there will be some failures, but we won't put all our eggs in one basket, right? So we'll have backups, we'll be prepared for disasters, we'll be prepared to adapt. Another is trying to create incentives for more secure products. Another is training, because the weakest link today is still the human link. It's the person who clicked on that email or clicked on that attachment that they shouldn't have clicked on. The person who gets manipulated into leaking information that they shouldn't manipulate. The person who chooses a really easy password. All of those things are what ultimately compromise security. And you can build the best technology in the world, and if somebody tells the wrong person their password, you've got a problem. So that human dimension, the training element, is also something that we always have to focus on. Ultimately, software is based in social institutions and social organizations. It's organizations that build it, that design it, and that use it. And so it's the social dimension that ultimately underlies a lot of vulnerability.
Excellent. I think that covers everything I wanted to say.
Great.
Thanks a lot for coming.
Thank you very much for having me.
And thank you for listening. Bye.